2. Introduction. Mostly, an experimenter has an interest in those outcomes that occurs in a random experiment. Then the next question that arises: how to compute them, i.e. computation of these outcomes. Probability definition and probability concepts are used to find these outcomes and their numerical measure in terms of probability. If an experimenter is only interested in number of outcomes in a random experiment and computation of number of outcomes instead of type of outcomes, then both random variable and probability distribution concepts are used. Suppose n dice are thrown in a random manner. The experimenter wants to know about the sum of coming points on the faces of the dice. These types of problems are solved by probability concepts and definitions which have been already discussed previously in the modules related with probability. Suppose n coins have been tossed randomly. The experimenter is interested in to find out the number of tails obtained while tossing a coin. When such type of event occurs, experimenter has an interest in association of random numbers to these upcoming outcomes. The association of random number to each outcome is known as random process, and random association is known as random variable. Distribution of random variable and its probability is defined as probability distribution. Probability distribution will be used to find probability and other properties of random variable like mean, median, variance, moment generating function, etc. Sometimes random variables are used several times. To make these random variable useful for practical purposes, then mathematical expectation is used. Suppose a businessman wants to know his average profit on a commodity. A cancer specialist doctor wants to know his average number of patients diagnosed with successful treatment. Mathematical expectations are used to solve these types of problems. Random variable, probability distribution, and mathematical expectation are the most important terms that are used in the probability theory. These terms are also used in programming language to find out the characteristics of the data. In programming languages, these type of properties are defined as summary of the data. In summary, many properties of the data are included like variance, mean, expectation, mode, median, quantiles, quartiles, minimum value, and maximum values. Let's discuss more in detail about random variable, probability distribution, and mathematical expectation. In the next section, we first define the random variable and its mathematical expression. After that, different types of random variables are also discussed. 3. Random variable. 5. Statistical applications in environmental sciences. One thing will strike in your mind when you listen the word random variable first time. One may assume that the random variable is a variable that is not absolutely correct. One can have controversy with its name. Random variable is a function instead of just a variable. Function is relation between two well-defined sets. One set is known as domain and second one is range. Similarly, random variable is relation between two sets. One is set of possible outcomes, i.e. sample space, and second one is subset of real number. Set of possible outcomes is known as domain and subset of real number is known as range. Random variable is a function whose domain is a set of possible outcomes and range is a subset of the set of real number. Random variable is normally denoted by capital letter like A, W, S, Z, U, P, dot, etc. And outcome of random variable is denoted by small letters like A, S, C, X, Y, Z, P, etc. 3.1 Mathematical expression. Say X be a real number connected with the outcome of a random experiment E, S be a sample space of the random experiment E, and Z represents the each outcome of the experiment E that comes from sample space S. X, Z represents the real number to each outcome Z, is known as random variable. A random variable X, Z is a function whose domain is sample space S and range is the subset of set of real number infinity, infinity. For example, tossing a coin 3 times at random is a random experiment E. Let us define random variable as a function for counting the number of heads 0, 1, 2, 3, or to count the number of tails 0, 1, 2, 3, or to count the number of head tail appears at first place in a random experiment E. Here we define the random variable as a function to count the number of heads 0, 1, 2, 3 that occurs in an experiment. S equals HHH, HHT, HTT, HTH, THH, TTH, THT, TTT. Each outcome of the sample space is represented by Z. Random variable X, Z is X, Z equals H equals 0, 1. H equals 1, 3. H equals 2, 3. H equals 3, 1. When number of head is equal to 0, random variable X, Z equals 1. When number of head is equal to 1, random variable X, Z equals 3. When number of head is equal to 2, random variable X, Z equals 3. When number of head is equal to 3, random variable X, Z equals 1. Remarks. 6. Statistical applications in environmental sciences. Linear function of the random variable is also a random variable. Suppose X and Y are two random variables. Following 3 linear functions of 2 the random variable are also random variable. 2x plus 5y, xy, x plus y. If x is a random variable, then I1 x, e x, e max x1, x2, I b min x1, x2 are also random variables. A continuous and increasing functions of a random variable are also random variable. 4. Types of random variable. Suppose the number of students in a class is 50 that shows whole number and height of students that may lie in some interval because it may be 4.5 or 6.1 or 5.5 inch. According to examples, a random variable may be associated with either a finite countable number, as well as infinite countable, i.e. discrete value, or infinite uncountable interval, i.e. continuous values. Random variable is classified as of 2 types: first as discrete and second one as continuous values of variable. 4.1 Discrete random variable. Discrete data means integer data that mean it does not include decimal values and considered only whole values. Discrete values can be positive or negative. For example, plus or minus 1, plus or minus 2. Discrete random variable is a random variable which assume only finite and countable values. List of some examples of discrete random variable. Number of phone calls in a day. Number of road accidents in a day. Number of claims in a day. Number of job seekers for a data scientist job. Number of grammatical errors in a text. Number of customers in a showroom. Number of defective products in a manufacturer company. Number of produced products by a manufacturer company. 4.2 Continuous random variable. Continuous data means real numbers that include decimal values. Continuous values are like as 2.3, 5.6, 9.8, 8.7. Or any value in any interval 1, 3, 7, 9, etc. These interval may contain infinite values between interval limits. 7. Statistical applications in environmental sciences. Continuous random variable is a random variable which can take any value in a given interval. List of some examples of continuous random variable. Closing price of share market. Temperature of metropolitan cities on a particular day. Distance traveled by a truck driver. Time taken by a bus service in traveling from Jaipur to Bathinda. 5. Probability distribution function. Frequency distribution is used to arrange repetitive data in an appropriate manner. For example, claims reported each day for 1 week is given as 0, 1, 2, 1. This dataset have repetition of some values. In this dataset 0 occurred 2 times, it means frequency of 0 is 2. Frequency denotes the number of data values occur. Another representation of the dataset is called frequency distribution. Claims. Each day. Frequency. This frequency distribution shows the distribution between frequencies shared in the dataset values. Probability distribution shows the distribution between probabilities and data values like frequency distribution. For example, tossing a coin 2 times and random variable x denotes the number of heads. Probability distribution of x is given as possible outcomes HHHTTH 1. 4 plus 1. 4 equals 2. 4 equals 1. 8. Statistical applications in environmental sciences. Px equals 2 equals 1. 4. Probability distribution is a function which distributes the probabilities of a random variable to each outcome of random variable. Mathematical representation. Suppose random variable is x and outcomes is z, then probability distribution function PDF is given as Px is less than or equal to x equals Pz, xz is less than or equal to x, where minus infinity less than x less than infinity. This is also called distribution function and cumulative distribution function. Probability mass function. If x is a discrete random variable and z, s are outcomes, then function pxz is given as pxz equals pzi if z equals zi for all I equals 1, 2. 0 otherwise function pxz is called probability mass function PMF of random variable xa function will be called probability mass function if it follows following conditions. I pzi is greater than or equal to 0 for all I. En array summation pzi equals 1 infinity. I equals 1. For example, rolling a dice which has 6 possible outcomes so s equals 1, 2, 3, 4, 5, 6. Let x be the random variable defined by x equals 1 if even number face of dice occur. 0 otherwise px equals 1 equals 3. 6 equals 1. One can see that this function is probability mass function, as it satisfies the condition of probability mass function. IPZ Px is less than or equal to x equals Pz, xz is less than or equal to x, where minus infinity less than x less than infinity. This is also called distribution function and cumulative distribution function. Probability mass function. If x is a discrete random variable and z, s are outcomes, then function pxz is given as pxz equals pzi if z equals zi for all I equals 1, 2. 0 otherwise function pxz is called probability mass function PMF of random variable xa function will be called probability mass function if it follows following conditions. I pzi is greater than or equal to 0 for all I. En array summation pzi equals 1 infinity. I equals 1. For example, rolling a dice which has 6 possible outcomes so s equals 1, 2, 3, 4, 5, 6. Let x be the random variable defined by x equals 1 if even number face of dice occur. 0 otherwise px equals 1 equals 3. 6 equals 1. 2. Px equals 0 equals 3. 6 equals 1. 2. One can see that this function is probability mass function, as it satisfies the condition of probability mass function. IPZI is greater than or equal to 0 for all I. En array summation PZI equals 1 infinity. I equals 1. Graphical representation. 9. Statistical applications in environmental sciences. The graphical representation of probability mass function of the random variable is given in the figure 1. Figure 1. From the figure 1, we can see that on the x-axis we have discrete point 2, 3, 11 and on the y-axis the corresponding probabilities are given. So if add up all the probabilities the sum should be equal to 1. Graphical representation of distribution function for the discrete random variable is presented in the figure 2. Figure 2. 10. Statistical applications in environmental sciences. Some question with solutions are given here for better understanding. Question 1. 2 dice are rolled. Let x be a random variable which is sum of upturned faces is even. 1. Construct probability distribution table. 2. Find the distribution function of x for 1 i.e. f1. Answer. 2 dice are rolled in a random experiment. Sample space is S equals 1, 1, 1, 2, 1, 6, 2, 1, 2, 2, 2, 6, 3, 1, 3, 2, 3, 6, 4, 1, 4, 2, 4, 6, 5, 1, 5, 2, 5, 6, 6, 1, 6, 2, 6, 6. Random variable x is given as x equals 1 if sum is even. 0 if sum is odd. Outcomes of random variable x are x equals 1 equals 18. X equals 0 equals 18. Probability mass function of the random variable is given as p x equals 0 equals 18. 36. P x equals 1 equals 1836. Function satisfies the condition of distribution function. IPZI is greater than or probability density function. If x be a continuous random variable and z outcomes comes from a, b interval, area under this interval will be called as probability density function PDF. Probability density function or PDF of x will be shown as fxz. Pa is less than or equal to x is less than or equal to b equals integral fz dz. B. A. A function will be PDF in interval if minus infinity function satisfy the following conditions. IFZ is greater than or equal to 0. E integral fz infinity. Minus infinity dz equals 1. EPE equals integral fz dze. Where E is any event of random experiment. Remarks. Probability value of any constant c is 0 for continuous random variable. P x equals c equals 0. For all CPA is less than or equal to x is less than or equal to b equals PA less than x is less than or equal to b equals PA is less than or equal to x less than b equals PA less than x less than b. Continuous distribution function. 0. 0.05. 0. P. Statistical applications in environmental sciences. If x is a continuous random variable with PDFFZ, the function is fxx equals p x is less than or equal to x equals integral fz. X. Minus infinity. dz, minus infinity less than x less than infinity. The function fxx is called distribution function or continuous distribution function. Question 3. A continuous random variable x has the PDF fxz equals me minus 3z. For z is greater than or equal to 0, find the value of m and p x is less than or equal to 8. Answer. Since integral fz infinity minus infinity dz equals 1. Integral me minus 3z. Infinity 0. dz equals 1. M integral e minus 3z. Infinity 0. dz equals 1. Type. Me minus 3z. Minus 3. 0. Infinity. Equals 1. After putting the upper and lower limits on the integration, m asterisk operator. 1. 3 equals 1. M equals 3. Now to find the value of px is less than or equal to 8. Px 15. Statistical applications in environmental sciences. Once PDF for the random variable is determined, often one wants to compute expected value or average value of random variable. Expected value for a discrete random variable is a weighted average, where weight is the probabilities to the associated random variable values. Mathematical expression for the expected value of discrete random variable x with probability mass function PMFFZ. Ex equals n array summation ZFZ. C. Dot. Mathematical expression for the expected value of continuous random variable x with PDFFZ. Ex equals integral ZFZ. Infinity. Minus infinity. dz. Note, expected value for the random variable exists of right-hand side of mathematical expression is convergence, i.e. finite value of the variable exists. Properties of expectations. 1. Expected value of function of random variable is same as the expected value of the random variable. Mathematical expression for the expected value of function of discrete random variable gx is given as gx equals n array summation g zfz. C. Dot. Mathematical expression for the expected value of function of continuous random variable gx is given as gx equals integral g zfz. Infinity. Minus infinity. dz. 2. If the expectation of two random variable x and y exists, expectation of addition of two random variable is equal to addition of expectation of respective two random variable. Mathematical expression is given as Ex plus y equals ex plus ey. This property also holds for function of random variable. 16. Statistical applications in environmental sciences. 3. If the expectation of two random variable x and y exists, expectation of multiplication of two random variable is equal to multiplication of expectation of respective two random variable. Mathematical expression is given as. This property also holds for function of random variable. Exy equals exey. 4. Expectation of any constant is equal to the constant. Let us suppose c is any constant value, then mathematical expression is given as c equals circa. 5. Expectation of linear combination of random variable or function of random variable is given as x plus c equals ax plus c, where n c are two constants and x is a random variable. Moments. Moments are used to find basic calculations of mathematical statistics and probability distribution like mean, variance, skewness, and kurtosis. Mean is first central about mean, variance is a second central moment about mean, skewness is ratio of square of third central moment to cube of second central moment about mean, and kurtosis is ratio of fourth central moment to square of second central moment about mean. Mathematical expressions for the moments are given as the RTH central moment about mean of a variable x given as mu r equals n area summation she minus x r n I r equals 1 2 n r, where n area summation fi equals ni. The RTH moment about any point A is mu r equals n area summation she minus a r r n I r equals 1 2 n. When r equals 1 2 3 4 moments are mean equals mu 1 single quote semicolon var equals mu 2 equals mu 2 minus mu 1 2 mu 3 equals mu 3 minus 3 mu 2 mu 1 plus 2 mu 1 3 mu 4 equals mu 4 minus 4 mu 3 mu 1 plus 6 mu 2 mu 1 minus 3 mu 1 4. 17. Statistical applications in environmental sciences. Measure of skewness is beta 1 equals mu 3 2 mu 2 3. Measure of kurtosis is beta equals mu 4 mu 2 2. Variance. Variance is used to find variability in the data. Variance is also called the second central moment. Variance can be defined in the term of expectation. The mathematical form of variance is given as Vx equals ex2 minus ex2. If a and b are two constants, variance of linear function given is Vx plus b equals a2bx. Variance is affected by change of scale but not affected by change of origin. Question 4. Let x be a random variable with the following PDF. Fx equals 3x2, for 0 less than x less than 1. Vx equals 0.4125. Hence Ex is 0.75 and Vx is 0.4125. In this section, we discussed mathematical expectations of a random variables. Moments and their mathematical forms are also discussed. Some solved questions are included for better understanding. 7. Summary. In this module, we first give an introduction to random variable. Two types of random variables are also discussed with examples. A function is said to be probability mass function, probability distribution function, and distribution function of random variables if it satisfies some conditions n. 19. Statistical applications in environmental sciences. These conditions are explained in detail. Also, mathematical expectation of the random variables are also discussed. 2. Introduction. Based on the information that we already discussed in the modules of probability theory that enables one to fit a mathematical function on the observed data in terms of probability distribution function PDF of the random variable of a random experiment. If the random variable is to follow some properties of the particular probability distribution function, then it is easy to find out qualitative measure of the random variable like mean, variance, skewness, and kurtosis. It is possible to formulate these type of random variable according to specified law either on the basis of condition or on the basis of results. Suppose outcome of random variable or equally likely, possible outcome of random variable or 2, then it is very easy to find out the probability values, but when the number of outcomes are more and it is difficult to find out the probability for a rare happening event in an experiment. These types of particular problem can be solved by using specified probability distribution functions. In this module, discrete distribution function are discussed with their properties and mathematical expression of the probability distribution function. The distributions that we will discuss in this module will be only for univariate case. Univariate is basically refer to mathematical function or equation that is defined only for one variable. In literature, distribution for two random variables and more than two random variables are also discussed, but we restrict ourselves in this module only to one variable. As we already discussed about the types of random variable, discrete or continuous random variable in the module, Introduction to Random Variable and its Properties. In this module, our main motive will be to give an introduction to distribution of discrete random variables. Some of the most commonly used discrete distributions in literature are given as discrete uniform distribution, Bernoulli distribution, binomial distribution, Poisson distribution, negative binomial distribution, multinomial distribution, geometric distribution, and hypergeometric distribution, etc. Properties of these discrete distribution functions will be discussed like expectation, mean variance, skewness, kurtosis, and PMF function. In the module, Introduction to Random Variable and its Properties, we discussed about the mathematical formulation as well as properties of expectation, variance, skewness, and kurtosis. We also discussed about the properties of a probability distribution function. In this module, we will again discuss about moments, skewness, and kurtosis, but now we will derive these properties for defined discrete distributions. 3. Discrete uniform distribution. 5. Statistical applications in environmental sciences. Discrete uniform distribution is used when outcome of random experiment is equally likely. For example, tossing a coin, rolling a dice, selecting a deck of cards, etc. Suppose a random variable x is said to have a discrete uniform distribution with p, m, f, is given as p x equals z equals 1. N, for z equals 1, 2, n 0, otherwise. Where n is the number of possible outcomes. Z is the outcome of a random experiment. Mean. Ex equals n area summation z f z. C. Semicolon. Ex equals 1. N area summation I. N. I equals 1. Equals. N plus 1 2. Variance. Ex2 equals 1. N area summation I2. N. I equals 1. Equals. N plus 1 2 n plus 1 6. Vx equals ex2. Ex. 6. Statistical application. Number of diamond ace is 1. Then the probability of getting diamond ace is PE equals number of favorable outcomes, number of total outcomes equals MN. Hence PE equals 1. 52. Since probability of getting diamond ace is equally likely event, so this shows the PMF of discrete uniform distribution. Question 2. An example of a discrete uniform distribution is when throwing a 6-faced dice, what is the probability of getting one of the integer? Find mean and variance. Answer. Suppose a dice has 6 faces and x is a random variable that represent the outcome of a getting integer of them through function, x is the outcome of the event. Probability of getting one integer is p x equals 1. 6 for all x equals 1, 2, 6. This probability is equal to for all integer outcome of a 6-faced dice. Event getting an integer on the face of dice is considered as an equally likely events. Discrete uniform distribution is applicable for equally likely events. So we can consider the PMF of random variable x as discrete uniform distribution. As the mean of the discrete uniform distribution is given as n plus 1. 2. Mean of random variable x is given as ex equals 6 plus 1. 2 equals 7. 2 equals 3.5. Variance of the discrete uniform distribution is given as vx equals n plus 1 n minus 1. 12. Hence the variance of the random variable x that take integer value of dice is given as vx equals 62 minus 1. 12 equals 35. 12 equals 2.91. 7. Statistical applications in environmental sciences. 4. Bernoulli distribution. Bernoulli distribution is applicable for those random experiment who have only two outcomes like success and failure, head and tail, odd and even, profit and loss, etc. Two outcomes are considered as success and failure of the experiment. For example, tossing a coin is a random experiment and getting head is success and getting tail is failure. Rolling a die is a random experiment and getting even number is success and getting odd number is failure. Suppose P denotes the success of the experiment, Q denotes the failure of the experiment, X as a random variable is said to have a Bernoulli distribution with P, M, F, is given as P x equals Z equals F x equals P Z Q 1 minus Z, for Z equals 0, 1. 0, otherwise. Where Q equals 1 minus P. Often, random variable X takes value 1 for success and 0 for failure. Mean. Ex equals P. Ex2 equals P. Variance. Vx equals Ex2 minus Ex2, Vx equals P minus P2. Equals P1 minus P equals PQ. Question 3. Find the probability of getting sum of integers even in a rolling of two dice. Find mean and variance of the random variable. Answer. Total possible outcomes in a throwing two dice are 36. Number of even sum of integer faces in rolling two dice are 18. Number of odd sum of integer faces in rolling two dice are 18. Probability of getting sum of integer when the sum is even. It is given as P equals P x equals 18. 36 equals 1. 2 equals 0.5. 8. Statistical applications in environmental sciences. Since, here are two outcomes, one is getting sum of even integer and second one is getting sum of integer that is odd. Success of the experiment depends upon for getting sum of integer is even and failure of the experiment depend upon for getting sum of integer is odd. Random variable x is number of outcomes getting sum of even integer in rolling two dice. Random experiment have two possible outcomes, P and Q, success and failure respectively. PMF of random variable x is same as the Bernoulli distribution PMF. PMF of random variable x is given as P x equals Z equals 1. 2. 1. Opening parenthesis. 1. 2. 0. Equals 1. 2 for P equals Q equals 1 2. 0, otherwise. Where Z equals 0, 1. Mean for the Bernoulli distribution is given as Ex equals P. Variance of the Bernoulli distribution is given as Vx equals PQ, Q equals 1 minus P. Vx equals 1. 2 asterisk operator 1. 2 equals 1. 4. Hence we calculate that the mean is 1. 2 and variance is 1. 4 for the random variable x. 5. Binomial distribution. If a random experiment is performed repeatedly, each repetition is called as trial. Trial is called Bernoulli trials if number of trials are finite, trials are independent, probability of success is finite. Probability of success P is the occurrence of an event in a Bernoulli trial and Q is probability of failure is the non-occurrence of an event in respective Bernoulli trial. Distribution of repeated Bernoulli trials is said to be binomial distribution. Binomial distribution was developed by James Bernoulli in year 1700. Suppose a random variable x is said to follow a binomial distribution with probability of success as P, probability of failure is Q and n independent Bernoulli trials have probability mass function given as, where z is the outcome of the event. P x equals z equals cz. NP z q n minus z, z equals 0, 1, 2. N, q equals 1 minus p. 0, otherwise mean of the binomial distribution is given as 9. Statistical applications in environmental sciences. Hence, Vx equals n minus 1 p2 plus np minus n2 p2, Vx equals npq. Remarks. 1. Random variable x is follow binomial distribution with parameter n and p is denoted as x tilde b n, p. 2. Variance of binomial distribution is always less than mean of binomial distribution. 3. If x follows binomial distribution with parameter n and p, y equals n minus x follows binomial distribution with parameter n and q. 4. If x and y are two independent random variable and follows binomial distribution with parameter n and p, m and p respectively, x plus y also follows binomial distribution with parameter m plus n and p. This property is said to be additive property of binomial distribution. Mathematical expression is given as x tilde b n, p y tilde b m, p x plus y tilde b n plus m, p. Question 4. Suppose Ravi and Rahul play a game in which their chance of winning are in the ratio 4, 5. Find Rahul's chance of winning at least 5 games out of the 9 games played. Answer. Let P be the probability of Rahul winning the game and Q is the probability of Ravi winning the game. Then N equals 9. P equals 5/9. 10. Statistical applications in environmental sciences. Q equals 1 minus P equals 4/9. Hence by binomial probability law, the probability that out of 9 games played, Rahul wins Z games is given by Px equals Z equals CZ. 9. 5. 9. C. Opening parenthesis. 4. 9. 9 minus Z. C equals 0, 1. 9. The required probability that Rahul wins at least 5 games. Px is greater than or equal to 5 equals n array summation cz. 9. 5. 9. C. Opening parenthesis. 4. 9. 9 minus z9. C equals 5. Dot. By solving above equation, probability of Rahul wins at least 5 games is given as Px is greater than or equal to 5 equals 0.615. 12. Statistical applications in environmental sciences. 6. Poisson distribution. When event of a random experiment occurs at random point of time and space and our interest lies in the number of happening an event according to our interest, not in non-happening of event. Happening of an event is based on indefinite trials of an experiment. Suppose number of car accidents in particular time period, number of bus passing a crossing per minute during the festive season, number of faulty products in a lump of 100 etc. These type of problems can be solved by using Poisson distribution. Poisson distribution was developed by French mathematician Simeon Denis Poisson in 1837. Poisson distribution is used to count the happening of rare event in a random experiment. Poisson distribution is a limiting case of binomial distribution because Poisson distribution has number of trials indefinitely large, probability of success is very small. Since n right pointing arrow infinity and p right pointing arrow 0. Multiplication of n and p must be a constant. Let a be a constant then np equals a. Probability of success is given as p equals a n. Suppose a random variable x is said to have Poisson distribution with parameter and its PMF is given as px equals z equals e minus a z. C equals 0, 1. A greater than 0. 0, otherwise mean of the Poisson distribution. Ex equals n array summation z. Infinity. C equals O. E minus a z. C. Ex equals a. Variance of the Poisson distribution. Ex2 equals n array summation z2. Infinity. C equals O. E minus a z. 13. Statistical applications in environmental sciences. Vx equals a. Remarks. 1. If x is an random variable and a is constant, x follows Poisson distribution with parameter a is denoted as x tilde p a. 2. If x and y two independent Poisson distributed with parameters a and b respectively, then x tilde p a, y tilde p b x plus y tilde p a plus b. This property of Poisson distribution is known as additive property of Poisson distribution. This property can be extended to n events. 3. Poisson distribution is the only distribution whose mean and variance are same. 4. Let's say x and y are two independent Poisson variables. Conditional distribution of x given x plus y is binomial distribution. 5. Poisson distribution is a limiting case of binomial distribution. Questions. (15) (6) Geometric distribution. As binomial and Poisson distribution, we have independent number of trials or repetition have constant value of probability of success with varying probability of failure. Suppose one wants to calculate the probability of failure preceding one's success that can be calculated by using geometric distribution. Geometric distribution is a distribution that is used to find probability of failure preceding one's success. Suppose x is a random variable said to have geometric distribution with parameter p and probability mass function PMF is given as p x equals z equals q z p, z equals 0, 1. Q equals 1 minus p. This function is known as PMF of geometric distribution. Mean. E x equals n area summation z asterisk operator q z p. Infinity. C equals O. Semicolon. E x equals Q. P. Variance. V x equals E x2 minus E x2. E x2 equals n area summation z2 asterisk operator q z p. Infinity. C equals O. Semicolon. 16. Statistical. P2. Q. P2. Properties. 1. Variance of geometric distribution is always greater than mean. 2. Let's say x and y two independent random variable having geometric distribution, then conditional distribution of x given x plus y is uniform. Question 10. (7) Summary. In this module, we discussed about some very popular discrete distributions like discrete uniform distribution, Bernoulli distribution, binomial distribution, Poisson distribution, and geometric distribution. These distributions are among the most widely used distribution in the literature as well as its application part. We also discussed about their mathematical expression, properties like mean, variance, etc. In this module, we discussed about how to choose a particular distribution for a problem. Suggested readings. 1. Learning objectives. The main objective of this module is to give an introduction to some widely used continuous distribution. We will also discuss about the different continuous distributions. Some questions and answers are also included for better understanding. 2. Introduction. We are very well known that there are two types of random variables in probability. I.e. discrete random variable and continuous random variable. We are also much known to the fact that probability distribution is a mathematical expression of values of random variable that have specified probability attached with them under specific law. If random variable is discrete in nature, then the probability distribution function of variable is known as probability mass function PMF. Discrete random variable has distribution that follows some specific laws, properties, and generally termed as discrete probability distribution. There are some discrete distributions that have the features like probability of occurrence of each event is equally likely, discrete uniform distribution, only two outcomes, Bernoulli distribution, etc. The detailed discussion about the discrete distributions is already covered in the module, Introduction to Discrete Probability Distributions. On the other hand, if the random variable is continuous, then the probability distribution function of the variable is known as probability density function PDF. Continuous random variable has distribution that follows some specific laws, properties, and generally termed as continuous probability distribution. There are some important continuous random variable that we will discuss in this module. Some of them are uniform distribution, normal distribution, gamma distribution, beta distribution, exponential distribution, Cauchy distribution, etc. 4. Statistical applications in environmental sciences. Note, the probability of the continuous random variable for a specific value is 0. So the probability of all continuous random variables is calculated in interval. In this module, we will discuss not only about the continuous distributions but also try to differentiate them with their features and properties through graphical and mathematical representation, so that one can understand how to apply a particular distribution for a particular case. In this next section, we will discuss the most widely used continuous distribution, that is normal distribution. Normal distribution is the distribution that has the most practical applications in various fields. We will discuss various continuous distributions one by one so that one can easily differentiate them through their mathematical properties. 3. Normal distribution. Normal distribution is considered as the ruling model among the all continuous probability distributions due to its features and characteristics. It is considered as the important part of the probability theory in statistical analysis due to its features. The normal distribution was discovered by de Moivre, Laplace and Gauss. This is the reason that normal distribution is also known as Laplace distribution and Gauss distribution. Most of the distributions in probability theory tend to normal distribution when they have large sample size or have sample size greater than 30. If a random variable follows normal distribution, random variable is said to be normally distributed. Normal continuous probability distribution is widely used in social sciences due to its characteristics. As we already said that when the observations are very large, then by using laws of probability the data can be assumed to follow normal distribution. Hence normal distribution will help to extract information from the responses of the respondent in the questionnaire. Normal distribution is also used in linear and nonlinear regression modeling as the error terms in these models are assumed to follow normal distribution. Normal distribution has a vital role in inferential statistics. Normal distribution is the most widely used distribution in hypothesis testing, estimation and to find out the confidence interval of the parameters. Normal distribution has a wide application in parametric tests. Investment analysis, market analysis and risk analysis, biostatistics and environmental sciences are the other areas where normal distribution is widely used. Mathematical expression. Let us suppose y is a random variable and y is said to have normal distribution with parameter mu and sigma 2, which are the mean and variance respectively. Then the PDF of the y is given as fy, mu, sigma equals 1. Sigma square root 2 pi times express minus 1. 2 y minus mu sigma 2. Closing curly bracket. Where infinity less than y less than infinity, minus infinity less than mu less than infinity, sigma greater than 0. 5. Statistical applications in environmental sciences. The mathematical notation for a random variable y that follow normal distribution is given as y tilde and mu, sigma 2. Standard normal distribution. The standard normal distribution is a special case of the normal distribution with mean 0 and variance 1. As the probability of random variable that lie in an interval a, b, i.e. p a less than y less than b can be calculated in an exact manner because the integration cannot give a closed expression. To find out the probability value of continuous random variable for normal distribution with mean mu and variance sigma 2, we have to adopt the following method given below. To solve this problem, first we have to transform the normal variable to standard normal variable by subtracting mean value from normal random variable and divided by standard deviation. Then calculate the probability of this standard normal distributed random table from the table given in the literature. Mathematical expression. Suppose y is a normal distributed random variable, i.e. y tilde and mu, sigma 2, c equals y minus mu sigma, where z is a standard normal variable with mean 0 and variance 1, i.e. z tilde and 0, 1. PDF of standard normal variable z is given as phi z equals 1. Square root 2 pi express minus c2, 2. Where minus infinity less than z less than infinity. Properties. Normal distribution is a limiting case of binomial distribution if sample size is very large and right pointing arrow infinity. And probability of success, i.e. p, is very small. Normal distribution is a limiting case of Poisson distribution if average outcomes is very large. Lambda right pointing arrow infinity. Normal distribution is a bell-shaped curve and symmetrical distribution about mu. Also mean equals median equals mode. 6. Statistical applications in environmental sciences. Figure 1. IV. Normal distribution curve doesn't change the shape of curve if we change the mean, it simply move the position of the curve. V. If we change the variance of the normal distribution, that will change the peak of the curve. A smaller variance squashes and larger variance stretches. IV. Normal distribution curve doesn't change the shape of curve if we change the mean, it simply move the position of the curve. V. If we change the variance of the normal distribution, that will change the peak of the curve. A smaller variance squashes and larger variance stretches it. V. Odd central moment will be 0. Even central moment can be calculated by using this relation. Mu 2n equals 1.3.5, comma ellipsis. 2n minus 1 2n, n equals 1, 2. V. Sum and difference of two independent standard normal variables also follow a normal variable using the uniqueness property of moment generating function. If u and v are the two standard normal variable, if w equals u plus v and d equals u minus v, then w and d both follow normal distribution with mean 0 and variance 2, that is w and d tilde n 0, 2. Suppose yi are the normal random variable, linear combination of the random variable follows normal variable, i.e. n array summation ai yi tilde n, n array summation ai mu I, n array summation ai. 2 sigma 2. N. I equals 1. N. I equals 1. 8. Statistical applications in environment. 1. Properties. 1. Mean of the log normal distribution. Nine. Statistical applications in environmental sciences. P 400 is less than or equal to y is less than or equal to 600 equals P y is less than or equal to 600 minus P y is less than or equal to 400 equals 0.65. Hence the 5. Rectangular distribution. Rectangular distribution or uniform distribution is applicable for both discrete and continuous random variable. In this distribution, all the values that random variable can take in a given interval have an equal probability of occurrence. Discrete uniform distribution is a constant quantity whose PMF depends on the number of integers observations. The probability density function of the uniform distribution is also a constant quantity which depends on the length of given interval. The main application of the uniform distribution that is random number generation as well as p-value. P-value is the value that is used to make conclusion about the acceptance and rejection of the null hypothesis. In case of generating random number from any continuous distribution, first generate the random numbers from the uniform distribution that has interval 0, 1. Then equate the CDF of that particular distribution with the generated number from the uniform distribution and then find the required random number. Six. Beta distribution of type 1. Beta continuous variable having distribution of type 1 represents a family of probabilities and outcomes for proportions. For example, how likely is that current Prime Minister of India will win the next Prime Minister election? One of us few think that he will win, one of us think he will not think, and some of them think he will win or not. To solve this type of problem solution, beta distribution will be used. Beta distribution of type 1 is also known as basic beta distribution or beta distribution of first kind. There are many applications of the basic beta distribution like testing of Bayesian hypothesis, the rule of succession, task duration modeling, etc. A random variable y is said to have a beta distribution of first kind with parameter alpha and beta I. Y tilde b1 alpha, beta. The PDF of the beta distribution of first kind is given as Fy equals 1. B alpha, beta y alpha minus 1, 1 minus y beta minus 1, 0 less than y less than 1, alpha. Seven. Beta distribution of second kind or beta distribution of type 2. Beta distribution of second kind is also known as beta prime distribution and inverted beta distribution. Beta distribution of second kind is the odds distribution associated with a beta distributed random variable. Same as the basic beta distribution, the beta distribution of second kind is also used to model random probabilities and proportions. A random variable y is said to have beta distribution of second kind with parameter alpha and beta I. E. Y tilde b2 alpha, beta. PDF of the beta distribution of second kind is given as Fy equals 1. B alpha, beta y alpha minus 1. 1 plus y alpha plus beta, 0 less than y less than infinity, alpha, beta greater than 0. Properties of the beta distribution of second kind are I. Mean of the distribution is given as y equals alpha, beta minus 1. E. Variance of the distribution is given as 13. Statistical applications in environmental sciences. 8. Exponential distribution. A random variable that follows exponential probability distribution is used to describe the time between Poisson point processes. Poisson point process is a process in which events occurs continuously and independently at a constant average rate. It is also known as memory-less distribution. It is a particular case of gamma distribution. Exponential distribution is not same as the exponential families of the distribution. Exponential distribution has a wide application in reliability, stochastic process, etc. Exponential distribution is the only distribution that has a constant failure rate, so it has great importance in reliability. Exponential distribution is also used to find inter-arrival time in a homogeneous Poisson process. Exponential distribution is also known as negative exponential distribution. Let us suppose y is random variable that follows exponential distribution with parameter alpha. The PDF of exponential distribution is given as Fy equals alpha express minus alpha y is greater than or equal to 0, alpha greater than 0. The CDF is given as Fy equals 1 minus express minus alpha y. Nine. Gamma distribution. Gamma distribution is widely used distribution like normal distribution, exponential distribution. Gamma distribution is also related to the beta distribution. Problems can be seen in practical situations related to gamma distribution in processes where the waiting time for more than one person between Poisson processes. Suppose random variable y is said to follow gamma distribution with one or two parameter. PDF of gamma distribution is given as if y tilde ga, beta 2 parameter gamma distribution is given as Fy equals beta alpha e minus beta y alpha minus 1. Ga, y, alpha, beta greater than 0. If y tilde gamma alpha, 1 parameter gamma distribution is given as Fy equals e minus y alpha minus 1. Ga. Properties. I. Mean of the gamma distribution is given as, for 2 parameter case, y equals alpha. Beta. For 1 parameter case, y equals alpha. E. Variance of the gamma distribution is given as 15. Statistical applications in environmental sciences. For 2 parameter case, by equals alpha. Beta 2. For 1 parameter case, by equals alpha. E. Moment generating function is given as 1 parameter case. MYT equals 1 minus t minus alpha, t less than 1, IV. Poisson distribution and 1 parameter gamma distribution, defined above, have same mean n. Variance. B. 2 parameter gamma distribution's variance is less than mean. B. Gamma distribution tends to normal distribution as indefinite large value of parameter alpha. B. Gamma distribution follows additive property. Suppose there are y1, y2, comma ellipsis. Yn are the n gamma variables with 1 parameter alpha 1, alpha 2, alpha n. Then additive property of n random variables is given as n array summation yi tilde g n array summation alpha I. N. I equals 1. 1 dot. B. X. If x plus y tilde b1 alpha, beta. Relationship with the chi-square distribution. Gamma distribution is related with chi-square distribution, or we can say that for specific values of the parameters gamma distribution is transformed into chi-square distribution. When alpha equals nu. 2 where nu is a positive integer and beta equals 1. 2. Then the PDF of a chi2 distribution is Fy equals 2. Nu. 2y. 1. Answer. 2 greater 10. Cauchy distribution. Cauchy distribution is continuous probability distribution. Cauchy distribution is named on the French mathematician and physicist Augustin Cauchy. Cauchy distribution is also known as Cauchy-Lorentz distribution. Cauchy distribution does not have finite moments like mean, variance and moment generating function MGF. Mode and median of the Cauchy distribution are well defined. Cauchy distribution found in the field of working with exponential growth. Let us suppose y is random variable, then y is said to follow Cauchy distribution with parameter pi, with scale parameter s and location parameter t if the PDF is given as fy equals 1 s pi 1 plus y minus t s 2 closing parenthesis. If t equals 0 and s equals 1, Cauchy distribution is known as standard Cauchy distribution. The PDF of standard Cauchy distribution is given as fy equals 1 pi 1 plus y2 minus infinity less than y less than infinity. The curve of the standard Cauchy distribution will same as the standard normal distribution bell-shaped curve. Properties. I. Mean, variance, coefficient of variation and kurtosis are undefined. E. Mode and median will be location parameter t. E. Skewness is 0. 11. Summary. In this module, we discussed about some very popular continuous distributions like uniform distribution, normal distribution, gamma distribution, exponential distribution, beta distribution of 17. Statistical applications in environmental sciences. First kind, beta distribution of second kind and Cauchy distribution. These distributions are among the most widely used distribution in the literature as well as its application part. We also discussed about their mathematical expression, properties like mean, variance, etc. In this module, we discussed about how to evaluate probabilities for distribution through questions and answers.